So we're going to continue today talking and finish off the discussion of requirements, Chapter 4. I was thinking of getting into Chapter 5, but we won't. We'll just get it as far as Chapter 4. So let's just review a little bit. We talked about requirements, and we said that there are two main categories of requirements. The functional requirements, first of all, are those requirements that are explicit and obviously the ones that meet the customer's needs. They're the ones that the customer sees, the user sees as the functioning aspects of their system. So the inputs that they have to type or provide, or the outputs that are displayed, or the computations that are done that they're aware of, not how they're done, but what's done. And any timing issues associated with the system as well. Okay? These are the things that are functional in the sense that you have to provide computations and input processing and output processing to develop these. The non-functional requirements then are the ones that constrain the design. Okay? They're the requirements that basically tell you as a designer that, well, we have some objectives to meet. We know that we have to develop our functional requirements, but we've got to do that such that our system has a certain level of response time, certain throughput. It doesn't use too many resources, doesn't use too much memory. It has a certain level of reliability, and so on and so on. We don't want to over-constrain the design by making the response time and throughput and reliability too rigorous, because it'll cost too much. And we don't want to under-constrain by basically just not specifying these things or not giving quantifiable values, because then the designer won't know what to aim for, and we might not find that the system is useful for our end users. Okay? So we've got to balance these things, as with all aspects of requirements in software engineering. You know, what is the appropriate level of cost that we're prepared to spend for each of these things? Okay? In addition to those first set of requirements that or non-functional requirements that we call quality requirements, okay, quite often, we have a second set that we would call environment and technology non-functional requirements. These are saying what aspects of the design are going to be constrained according to, for example, the platform. You know, is the system going to always run on Windows? Is it always going to run on Unix, or both? What kind of operating system? What version of operating system? And taking a look in the future, where do we plan to extend this system to in the future? Maybe the first release is for Windows, second release is for Unix, or Linux, or something like that. And another related type of non-functional requirement is technology to be used. Okay? We don't want to tell the designer unnecessarily what programming language they should use, but we might have to say that, well, all of the other systems in this customer's environment are written using Java. Therefore, we must develop this system in Java, otherwise we're not going to be compatible with those other systems, and we're going to have people who have expertise in both Java and in, say, C++ to maintain the system. Okay? So often you want to constrain the technology. Maybe you've purchased an expensive piece of technology, say, for example, to provide web services. Okay? And so you want to make sure that the designer is designed for this technology and not for some other technology. Otherwise, you're going to have to purchase yet another technology. Okay? So these things are not directly things that, say, have to do with university registration, if it's a university registration system. But they're nevertheless important to the requirements. They're not functional in the sense that they're providing the functions that you want to solve the problem, but they're important anyway. Third category are constraints on the project plan and development methods. You might say that there is a certain published development method that you want all the developers in this organization to use, with the understanding that that is going to result in some kind of high-quality software. That might be, the customer might be very insistent that this be done because they want to guarantee that they're going to have a good quality product coming out in the end. They might want to insist that you be certified, ISO 9000 certified or something like that. Okay, ISO 9000, we'll talk about that later on. It's a standard approach to certifying that people are following certain quality standards. Another kind of thing that you might sometimes want to put in non-functional requirements is the delivery date and the maximum cost. Now, it turns out that these things are usually left and put as a separate document, as a project plan or a contract. And they're often separated out because basically the project plan or the contract says, we are going to develop these requirements within this cost and by this date. Okay, so that they separate those two things out. But logically, they nevertheless are, in some sense, an aspect of the requirements. They're things that constrain the designer. The designer has to design the system to deliver by a certain date and within a certain cost, typically in terms of the amount of human labor involved. Okay, any questions about the functional and non-functional requirements then? Okay. Now we're going to talk about a number of strategies and techniques that are used and are very important for people to learn who are going to be doing requirements gathering and analysis. Requirements engineering, as it's often called. We're going to talk about observation, engineering, brainstorming, prototyping. These are 4 key techniques that everybody should learn how to do. And all of these techniques involve interaction with customers and users and other stakeholders as well. So they're people-oriented techniques. Okay, they're techniques that require you not to be sitting in your office churning out code or writing documents. Okay? So software engineers have to be people persons, probably even more than other engineers. Okay? Because there's such a diversity of the kinds of problems and the kinds of users and the kinds of clients that software engineers have to deal with. But you really have to develop skills in interacting and negotiating and teasing information out of people and reaching agreement and stuff like that. Okay? The first class of technique is observation. And there are a number of things you can do with respect to observation. You can simply sit down and read things. That's observing documentation that exists of existing systems or requirements that have already been written by the customers, or wish lists, or any other kind of information that is in the documentary form or diagram form that would be useful for you to read. Secondly, we have shadowing. Shadowing is where you actively go and spend time with your end users, observing how they go about doing their work. Okay? So if my end users are, for example, people working in the registration desk or academic assistants in a university, and you're going to be developing a registration system, it would pay for you to sit in the office while this person is doing her or his daily work. Okay? While this person is talking to students, while this person is solving various kinds of sticky registration problems, shifting around the schedules of courses, changing the classrooms, all those kinds of things, to observe the kinds of things that they do and how they do them now. Maybe they use an old-fashioned system you're going to be replacing. Maybe some things they do by telephone, by instant messaging, by email. Okay, that'll give you ideas. Maybe you can automate some of these things. Or maybe if you don't automate them, at least your system has to be compatible with the kind of things that they do. It would be a big problem if you develop your system and then you gave it to the users and the users said, but gee, you know, we have to do X. And X is a very important part of our work, and you've made it harder to do X because you required us to be somewhere else or to be using some other system and we can't copy and paste or whatever. Okay? But if you'd sat down and observed them work, you would understand better how they really do their job and what their real needs are. Now that doesn't mean that you're going to implement a new system that is exactly a mirror of the way they do things today. Okay? It may very well be that you implement a system that has a totally new paradigm. But nevertheless, even in that new paradigm, there are probably going to be activities that the end users do that you're still going to have to fundamentally understand and fundamentally implement. So shadowing is an important skill, important technique. You don't need to do this in every single system. You know, it depends on the kind of system. But you should always consider it, especially if you've got end users who are doing a lot of work of different kinds. And, you know, you can really synchronize you to the way they think, the way they work, the problems they have. And give you a good rapport with the users for later on when you're negotiating requirements with them. You understand them because you've seen them work. A lot more software engineering organizations should consider doing shadowing. Even organizations, for example, doing simple thing, well, not simple things, but things which, like telecommunication systems, which are typically very complicated, but from the end user's perspective might be considered simple, like dialing a phone. Well, how do people work with telephones? A lot of software engineers don't actually, they use telephones themselves, but they may be using only a certain set of features. You should go and observe people doing sophisticated things like setting up conferences and working in call centers and things like that. Really understand how people do their jobs. You'll be a much better software engineer. Another major class of technique for observation is videotaping. This is stepping up to get one level greater in detail. Okay, now what we're doing is we're going and we're saying, okay, we can take notes. That's the shadowing approach. I often take notes using my computer. I'll go and sit down. In fact, when I was going back to shadowing for a second, I sat down with people when I was developing software engineering tools as part of my research. I'd go in, sit down, and watch people as they debug programs, as they searched for bugs, as they edited code, as they answered the phone, and as they chatted with the neighbor across the partition. I would write down everything in great detail of what they did. And because I had those detailed records of everything they did over the course of many hours, I was able to count how much time they spent on things. And I discovered that they spent a lot of time doing searching. Okay? And that was a realization that wasn't well known. We published papers, and we said, oh wow, now we know that maintainers do a lot more searching than we ever thought they did. They spend a huge percentage of their time doing searching. And the second most important thing they did was copying and pasting stuff. Just tons and tons of that. So we can optimize the tool to do better searching and make the process of transferring information from one place to another much easier. Unless we'd observed them, we wouldn't have got that. Videotaping can sometimes get you the same information, even more detail, and sometimes you need that extra level of detail. Okay? Any question about that? All right? So observation is something that's often not done enough of. Probably should do more. You should go out to organizations when you get your co-op jobs or your summer jobs or when you go out after you graduate and try and instill some of these techniques into your organization. You'll get better requirements out of it. Now, everybody has done interviewing. Interviewing is something that is a fundamental part of, always has been a part of requirements gathering, and you can't avoid it. And it's always been done. You just can't get requirements unless you do some interviewing. Okay? The thing is that we can do a better job of interviewing than is typical in industry. And as with all engineering processes, what you do to do a better job of interviewing is you approach the interviewing in a more disciplined, more systematic way than would be typical in industry. So, in the book, there's a lot of detail. I'm really going to summarize the interviewing approach here. And in fact, you can go and get other books that explicitly talk about interviewing as part of the project management process. But I'm going to give you a few tips. First of all, conduct a series of interviews. So you don't just do one interview, you interview a bit, you gotta go analyze the information, you come back, you interview more. And you interview different people. You try and interview many different types of users, many different clients. Sometimes you only have one client, many users. So you interview that client a lot over several times, over several weeks, and you interview various different kinds of users. You ask about both specific details and the broad vision. You're going to get different information. First of all, you want to try and get their detailed thoughts as much as possible. You want to get them to open up and tell you everything they possibly can about their ideas, what their problem is, what troubles they have, how many times a day they do this. You've got some of that through observation, but interviewing can give you a broader, here's what happens throughout the year kind of approach. You can't observe them for a year. You also get their thoughts about, well, I've always wanted such and such a feature, and I really wish our existing system would allow us to do X and Y and Z, right? That's the details. You want to coax out the details. Is there anything you've already wished for? And when they start talking about something, you say, can you give me any more details, any more thoughts? But here's a big warning. When you ask for details, don't give them the impression that you're going to go out immediately and implement all those details. That's extremely bad. Some software engineers go out and do requirements, and the user says, I want this and this. And they write it down and say, okay, great, we'll do that, we'll do that, we'll do that, we'll do that. you're not taking orders. You're not a grocer taking orders for fish. Okay? You're an engineer who is a professional gathering information to do analysis. You've got to consider it as gathering information. If you start saying, yeah, we'll do this, we'll do this, we'll do this, and then you go out and analyze and you realize that that's too much, that's too big, or that's technologically infeasible, or other clients and other users tell you different things, well, then you're going to have to go back to your first user and say, sorry, we can't do what you just said. And the first user is going to say, but you said you would. So don't commit yourself early on. Early on, it's information gathering. As time goes by, and you've got some drafts of the requirements, then you get to the point where you can start to negotiate. Then you get to the point where you can start to say, okay, well, you know, we've analyzed this a bit, and we've decided that it seems reasonable to do this and this, but this third thing here is going to take way too long. It'll take us 6 extra months if you want that. So what we'd like to do is we'd like to develop these first 2 things in the first release, get those out to you, and then work on this second part. And as part of the negotiation, the clients might well say, okay, you know, that's a reasonable compromise. Okay? We'll talk about approaches to compromising and approaches to negotiating in the brainstorming context and in the JAD context in a minute. You want to get the vision. The vision is like, if you had everything you ever wanted, how would it work? Or have you any dreams about how this system would work? You know? And they might not. You know? They might be totally unvisionary people. Okay, not everybody has a vision, but some people do. Some people have said, you know, I've been working in this organization for 20 years, and I've had every month had to spend a whole day doing this calculation. I'd really love it if somebody could automate this for me. And you say, gee, you know, that's it. In the back of your head, you don't say, yeah, we'll do it. But in the back of your head, you say, yeah, that's an obvious thing. No, you know, hadn't been mentioned, nobody else mentioned it, but it would take us half an hour development time. It's just a simple addition. You know, we've got the resources. It's not going to take us any extra work. And that saves that guy a whole day, a month, you know? So asking for the vision is a key thing that we really want to try and achieve. Okay? We'll get all kinds of ideas, sometimes wacky ideas, but sometimes those wacky ideas have things that are actually doable. Maybe the end users are only used to very boring applications, but they have a vision for wacky ideas. And those wacky ideas might be actually implementable. They don't realize it, but they might be. Ask if the users, once they've said what they think they'd like, you say, well, do you have any alternatives? Any other approaches you think might be reasonable? Or, you know, that way you suggested is very complex and might take an awful lot of development time. Can you think of any simplifications that would, or can we cut some things out of this? And they might say, yeah, sure. I mean, we don't really need all that stuff I've just spent the last hour telling you about. You know, if we just had this instead, that would solve most of our problem. You know? Well, unless you ask that kind of question, you're never going to get that kind of response. Therefore, you're never going to realize that you can save a huge amount of money. Another thing you can ask users and customers is, who else should I talk to? Maybe Jimbo down in the loading dock, you know? He's an eccentric, you know, who's been working there for years, and he goes off and studies astronomy and philosophy at night, but during the day he just sits and loads packages. But he's been observing everybody for years, and he knows stuff that nobody realizes he knows about the way this organization really works. Okay, so you go down and talk to Jimbo in the loading dock, you know, and he tells you stuff that you just otherwise would never have figured about things that go wrong. Okay, like he knows, you know, how inventory gets lost and stuff, and all kinds of things. He might also start talking about philosophy and astronomy too, but you have to try and get back on track if he does. And that is a problem, by the way, with interviewing customers and users. Often will go off track, so it's a skill to try and get people focused. The final point on this slide is get people to draw diagrams. Some people are visually oriented. They think visually about things. They're not very good at explaining things in words, or that's just not their mode of thinking. They think visually. Other people, on the other hand, think linguistically, and they don't think visually. And so there's a tendency in requirements gathering for people to get everything from the users in writing in words. And that will skip over some of the things that are better expressed visually, or the people who think better visually. So make sure that you ask, you have whiteboards available or flip charts or something, and get people, or just sheets of paper, and get people to draw pictures of things if pictures are reasonable in the context. Okay? Okay, so interviewing, a very important skill. You need to get more skill typically than the average software engineer has if you're going to do a good job of requirements gathering. Requirements failures are one of the biggest causes of software system failures. Okay? There have been systems that have taken a decade to develop and cost billions of dollars. I mean that. B with a capital B. Okay? Billions that have, the day they've been delivered, have been thrown away. Totally wasted. These are typically government systems, military systems, air traffic control systems, things like that. Why have they been thrown away? Thrown away either because of project management getting out of control, but largely that comes back to requirements. People didn't gather enough requirements, wrote wrong kinds of documents, we'll talk about that in a minute, didn't understand, didn't have enough rapport with the end users and the clients, didn't interact with them on an ongoing basis about what their real needs are, didn't respond to changes, we'll talk about that in a while. But a lot of this can be dealt with early on by doing appropriate interviewing, appropriate brainstorming, appropriate observation, and having a proper understanding of what the clients really need, and then breaking the problem down into small sections and delivering them bit by bit. So, this might seem, gee, got to learn this, but it's very important to do a good job of software engineering. Brainstorming, okay? Another key approach. Okay, so interviewing is typically involving a few people, maybe 1, 2 people. You don't want to interview large groups because it just takes too long and wastes everybody's time. Interviewing 1 or 2 people is good. Often 1. Brainstorming picks up. Brainstorming is good for 3 people, 4 people, but it's even better 5, 6, 7 people, and begins to become ineffectual when you get above about 12 people. You can brainstorm up to about 12 people, or more if you've got a really good moderator. Brainstorming is an approach where you get people to generate all kinds of ideas. Again, the wacky ideas that seem silly, whatever. People who are introverted are supposed to be able to participate as equals. They sometimes get drowned out by loudmouths in some environments. You want to design the brainstorming approach so that everybody has their say. All kinds of ideas can be put on the table at once. People can think about all kinds of ideas, and then you can go off and start analyzing them. Okay? So it's a group approach. The strategy I'm going to illustrate here is a strategy that I use. I've done some brainstorming consulting. I work with an organization as a consultant that actually does, their only business is organizing brainstorming sessions. And a lot of these techniques I learnt some years ago when I was working at Northern Telecom, Nortel, or BNR as it was then. So first of all, you need an experienced moderator, somebody who's been trained in these techniques and is able to exert some kind of authority because they know they know the techniques, they know how to run meetings, they know how to shut people up who are getting off topic or talking too much, and they know how to bring people in who are maybe introverted or don't normally want to speak up, and they know how to move the business on. Okay. Secondly, you need to get the people arranged around the table. Everybody's equal, so you don't have sort of somebody sitting at the head. Everybody's around the table, a round table, or something like this square table on this diagram works best. This is a small brainstorming session, but you can imagine more people. Everybody's around the table. The next point is you have what is called a trigger question, and this is a central thing to get right. A trigger question is a question which is open-ended. In other words, it doesn't have a yes-no answer. Okay? So, should we do X or not is not a good trigger question because some people answer yes, some people answer no, and you don't get any useful information aside from which won the vote. That's not brainstorming. Brainstorming is, what features should we develop in this system? What technological problems might we expect to run up against? What political problems might we expect to run up against in deploying this system among a large number of users? What solutions are there to a particular technological problem? And you specify what that problem is, of course. All these questions are types of questions that are open-ended because there are many possible answers that people can write down. And you're going to ask people to write down answers that are 1 sentence, maybe 2, but fittable on just a few lines of text, or maybe even a couple of words of text is even better, or a very short, quick sketch that people can sketch out in 10 seconds or 20 seconds or something like that. You don't want people to write long answers to these things. But the idea is to gather a long list, anywhere between 10 and 20, 30, 40 answers to the problem that are maybe slightly different from each other. Some of them might be radically different. Among those are going to be good answers. Among those are going to be answers that are thought-provoking. Some of the answers might be totally off the wrong track, but at least they've been brought out and people can write down this was no good. But in the brainstorming session, we try and keep everything open. We try not to say, that's no good. Okay. We try and just bring the ideas out into the open. So you have a trigger question, and then the moderator says, okay, everybody's going to write down on a sheet of paper, one sheet of paper per idea, their first thing that comes to their mind as an answer to the question. They write it down, a sentence, a sketch, a few seconds, 20 seconds, take a piece of paper and pass it on. Pass it on to their left, so clockwise around the table. So everybody's doing this, so everybody gets sheets of paper passed on from their neighbors. They look at the sheet of paper. Okay? So for example, let's say the fellow on the right-hand side of this diagram here, okay, writes down something, passes it on to his neighbor on the left. She looks at the picture and says, oh, okay, that's interesting. That stimulates some thought in my mind. Okay, I hadn't thought of that approach. That's not the approach I would use, but it gives me new ideas. Okay, so I'm gonna write down an idea now, and I'm gonna pass on both my idea and the idea from the fellow on the right on to the next person around the table. And that person gets to see all the ideas that come around the table. So all the ideas go around the table once, and they come back to their originator. Okay. So everybody's glanced at these things. They don't necessarily know who they come from. They might recognize handwriting, but that doesn't really matter. The point is that everybody's working in parallel a little bit at first. So it's efficient. Everybody's working in parallel rather than one at a time where everybody has to wait. Everybody gets to read ideas from other people, nevertheless, so there's still a cross-fertilization of ideas. And at some point in time, the moderator sees that people stop writing and stops it. So maybe after 5 minutes, maybe after 10 minutes, maybe even longer, but it's up to the moderator has to be skilled in that. The moderator stops the brainstorming process of the paper passing and then says, now we're going to start talking. And so the moderator asks people one at a time around the table to please read out and explain briefly one of the ideas that they have in front of them, typically one of their own ideas. Maybe an idea from somebody else. Doesn't really matter. But explain, what this idea is, maybe a few words as to what the impact of this idea would be, but they don't be harshly critical and say this is useless. We're going to leave that till later. Okay, so the ideas are brought out. Everybody has thought about the ideas a little bit. Maybe some people ask questions. The moderator has to control that. After another 10 minutes, maybe 15, 20 minutes, the moderator says, okay, I think we've brought enough ideas out onto the table now. Typically, he or an assistant has been writing them down on a whiteboard or flip charts. Okay? Often the next step is to take a vote. Okay, which of these ideas is the best? There's different strategies for voting. Maybe everybody gets 5 votes and they can put those 5 votes by any idea they want. And then you tally up the number of votes by each idea in the end. Or everybody gets 1 vote, or there's different strategies of voting, different ways of doing it. Okay? And the moderator can pick the voting strategy that would work best in each circumstance. In the end, then you get a prioritization of the ideas. Or maybe you get the best idea, and that's the one that you're going to decide to implement. Okay? And then you can go on. Maybe this has taken half an hour, 40 minutes. You go on, maybe you have a second brainstorming session with a different trigger question. Okay? That's probably going to be enough. An hour and a half, 2 hours is kind of the limit for these kinds of things. People get tired. Question?
Yes, I'm just wondering if the software engineer should be the same person as the moderator, or is it better if the engineer is not even there at all during the brainstorming session?
Oh, no, absolutely the engineers should be there. Because the engineers have to participate. Remember, they're stakeholders. The software engineers know about technological things. They have been doing some of the early stages of requirements analysis. They've maybe done some basic interviews. They have some knowledge. Sometimes the software engineers know more about ideas than the users and customers because the software engineers have been talking to everybody. Sometimes the customer hasn't talked to anybody. Just has an idea in their head. So the software engineer being there is very important. They can contribute ideas quite often. And they can also have a perspective on the technological solutions as well. I mean, we're not going to, in this state, brainstorming about design, but nevertheless, understanding what's feasible and what's not can be quite important. And also, the software engineer, having seen other kinds of software out there, can also bring up ideas that the end user would never have thought of because they don't realize some options available. The other question was, should the software engineer be the moderator? Well, the answer is that depends. It can work. You can run brainstorming sessions in small organizations where practically anybody can be the moderator, and the moderator can also participate in the going around the table. That's optional. I don't do it that way myself when I'm running them, but it can be done in a small organization with less formality. The moderator still has to decide when, the sequencing, when to start, when to stop, but can contribute some ideas at times. And in that case, the software engineer could be the moderator. But where possible, it's probably preferable to have somebody who is a bit off to the side, a bit uninvolved with this project, to be the moderator. But nevertheless, the moderator has to know enough about what's going on to be able to get an appreciation for whether things are getting off track or not. Okay? Any other questions? Joint application development is another approach that makes extensive use of brainstorming. In joint application development, traditionally, people have gone off out of town, certainly out of their offices, so they're in some other environment, and they spend maybe a whole week, certainly 2 or 3 days, all the stakeholders together, hashing out the requirements. Okay? Sometimes even going beyond the requirements, working out some prototypes as well. Although we'll see in a few minutes that that's part of requirements gathering. The idea is that everybody is uninterruptible. They're in a different place. They're not going to get phone calls. They're dedicated to negotiating requirements and working out what the needs are. They might break into subgroups to work on particular features in particular areas, get back together again. The end result of a joint application development session is a requirements document. Okay? So that's a technique that is often used in organizations, and it can be quite effective. People tend to get much more work done when they're off in a retreat away from their regular work, uninterruptible and in a different environment. So you can often get these things done faster than if you were trying to do this while everybody's getting on with their normal work. Prototyping then is the 4th major class of requirements gathering technique. Many people do this in the software engineering world. Behind interviewing, it's probably the 2nd most common technique that's used. I think all 4 techniques should be used almost always, by the way. Most prototypes are of the user interface, because the user interface tends to have more what are called degrees of freedom. There are more things, the more options, more alternatives that we need to consider, okay, in the user interface context than, say, in an algorithm design context. You can once you've done the specification and worked out the boundaries among subsystems and so on, you can give a software engineering team or an individual software engineer the responsibility of working out the requirements, the design of the algorithms and databases and things like that. And yeah, there are some design decisions and alternatives, sometimes quite complicated alternatives, but they'll be able to work them out based on solid engineering principles. Whereas at the requirement stage, and the user interface stage in particular, there's just so many possibilities. You've got to play around with these possibilities with the end users. Okay? With algorithms, you can play around with algorithms and the computer's going to tell you which one works fastest. Okay? With the prototypes, with the user interface, you've got to play around with the users to figure out which ones seem to be the best, which the users understand best. I mean, I teach user interface design, and I have just recently been blasted for creating a really lousy user interface for a website that, I realized what the problem was, and some users liked it, but there were some users that really hated it. It was a quick job. It was only going to be used by about 30, 40 people for one invocation, so we didn't invest a lot of time in it. Probably wouldn't have been worth doing extensive prototyping. A few people hated it. Well, too bad. I just typed the data in myself, Saves me. In the end, that's the cheapest solution there. The point is that prototypes, systems which are going to be used by large numbers of users over a lot of time, are important to work out the wrinkles. You just don't know what really goes on in people's heads. They've got to play with the system and give you feedback on it. You can start off using just a paper prototype, where you just draw pictures literally on sheets of paper and walk users through scenarios very early on after the first few interviews, and you can really stimulate a lot of ideas about the kind of input and the kind of output that users think would be appropriate under those circumstances. You can move on to a mock-up of the system written in some rapid prototyping language, Visual Basic, Java but drawn using a toolkit that puts together sets of windows rather than coding from scratch. Avoid user interface prototyping using low-level languages like C, C++, because that's going to take you a long time and it's going to be complicated and bug-prone, and that's what you're going to maybe do in the final design. But in prototyping, your answer is to cook something up that you can cook up in anywhere between a few minutes and a couple of hours, so that you can play with it and throw it away. Okay? If it takes you 5 days and you play with it and throw it away, it's a waste of time. So you want to play with it and throw it away, or be able to make radical changes. We're not going to focus on the underlying parts of the system, the algorithms and so on. That's we leave until later on. In fact, generally speaking, our prototype is going to be thrown away. It's used for gathering requirements, and then we go and come up with the real system. And that's where we put the solid engineering effort into designing it right. Prototype is used to gather requirements. Okay? Questions about that? It's also possible to prototype other than the UI. You can prototype algorithms. Okay, if you don't know whether a particular problem is solvable algorithmically in a reasonable time, you might go and do some mathematical analysis of that, or you might go and do some prototyping. Okay, before you get into the real design of the system, to see whether feasibly we can do some calculation within the response time requirements. But most prototypes are of the UI. We're going to talk about UI design to some extent when we get into Chapter 7, although the main subject will be discussed in another course. Okay? It's not really the core subject of this book. Another thing we'll talk about in Chapter 7 is use case analysis. This is the 5th technique of requirements gathering, and it's the technique that is very popular and talked about a lot these days. Basically what a use case is it's a sequence of steps that the user does something, the system responds. The user does something else, the system responds. The user does something else, the system responds until the end of that sequence. It's a path that the user uses through the system. There will be many different paths through the system doing different things. So, for example, in a registration system for a university, one type of user is a student, and the student has many use cases, potentially. One use case might be the user starts off knowing they want to register in a course, SEG 2100. They know they want to register in it, they just have to go in and press the right buttons. So, the use case says, they log in, the system responds to that. They press the button that says register in course. The system responds by bringing up a list of courses. They click on the course SEG 2100, the system responds, here's the details of 2100, are you sure you want to register? The user clicks OK, the system says confirmation that you've registered, please print out this for your records if you want, here's a confirmation number. The user clicks OK, and that's it. Okay? That could be a use case. Now, that's a bit specific to a particular design, so often these user interface designs, so often these things are done in a more generic way. We don't talk about clicking on particular things. I'll try and leave that till a little bit later on. But nevertheless, it's a sequence through the system where I do very specific things. Display a list of courses, select a course, confirm the selection, and I'm done. Another path through the system might be much more sophisticated. Another path might be, I'm decided to switch into software engineering. I know that as a specialty in software engineering, I want to focus on project management. So I want to make sure that I've opened up as many courses in management as I can in my 4th year. So I go into the system. I just choose the option that says, optimize my program for particular courses. I specify courses that I want to register, I want to take later on in my academic career, in my 4th year, let's say, and the system remembers those, and then I say, then I click on the button that says, suggest courses I should take now. And it gives me a list of courses that I should take now in order to make sure I can take those other courses later on. And then I have to pick a subset of those because I can't necessarily I have to make some choices maybe. And then I say register in all these courses, and the system goes and acknowledges. Another use case might be I try to register in a course using one of those strategies, and the system says, the course is full, you can't do it. Okay? And that's a use case that is explaining a path of the system that gives rise to an error situation. Okay? Often you have many different paths through the system, each of one is a use case. And the concept is that by describing your requirements in terms of use cases, you've made sure you've covered everything the user wants to do. You also need to cover everything that all the different kinds of users want to do. We call the different kinds of users actors. That's the technical term used. So one kind of actor is a student. Another kind of actor is academic assistant who helps you register and gives you advice. Another kind of actor is the professor who wants to look up information about registration. And the fourth kind of actor is the registrar who adds courses, changes descriptions, sets the schedule, and so on. Okay? And we have use cases for all of these. In Chapter 7, we'll see more details, but I wanted to bring it up now because fundamentally it is a core requirements gathering technique. Any questions? I urge you to take a look at the book and start thinking about these aspects before we get to Chapter 7. Alright, so we've gathered and analyzed requirements using those techniques. This is a major software engineering activity. Okay? A lot of work goes into this. It's critically important to get this right. We have to, however, somehow write our requirements down. And this is where we often fall down. Sometimes people don't write the requirements down at all, or just sketch them out, and then people who go and develop the system don't really understand what was needed. Other times, people write down 10,000 pages of requirements, quite literally, with big government military systems. That can be the number of pages. And that can be excessive. We have to right-size our requirements, get the right level of documentation, not too much, not too little, so that we have an optimum cost-benefit balance. Okay? So one of the things to look at, first of all, is we have two levels of requirements. The end users level, which end users can really understand and really agree to, because they understand what you're saying. But sometimes we need to go to more detail. The more detailed level of requirements will be more specific, especially if we have interfaces to other systems, client-server protocols, things like that which have to be in the requirements. End users are not going to understand that, so we can't expect them to. I am going to classify these as definitions for the end users, specifications which are more technically oriented. Still requirements, not design, but more technically oriented. End users will have trouble in some cases understanding these, and so we need both kinds often. When you go to companies, each company has its own standard. And you have to adhere to the standards defined in that particular company. Okay? So you might find that in, say, Nortel, they call them FNs and FDs and things like that. Okay, well, that's fine. But just the concept of different levels of detail is an important concept. Secondly, not only do we have different levels of detail, but we have different subsystems and sub-subsystems. So the diagram on page 16 is showing that we might have a requirements document for the system as a whole that is in broad strokes saying what's needed. Main functions that are needed by the system. Then we divide the system up into subsystems. And so let's say we have one subsystem that is the student browsing subsystem for our registration. And that might be broken down into different requirements for different features. We have one requirement for the basic registration feature and one requirement for the advanced feature which gives user active suggestions to help them pick courses that will meet their desires in fourth year. And that's a different subsystem that has different types of screens and different kinds of calculations. And each of these might have both a definition and a specification. Over on the other side, we might have a subsystem for the registrar, for adding courses and deleting courses and changing descriptions and things like that. Different part of the same system, different subsystem, so we split up and have a separate requirements document for it. Okay? And we might decide that we're going to deliver the requirements of this subsystem earlier and the second subsystem at a later time, or vice versa. Okay? How much detail? How much work should we go into producing sophisticated, long, detailed requirements? Or maybe we should make it somewhat quicker and dirtier and just sort of sketch out use cases and call it a day. You can do either, and it really is a question of cost-benefit, and really a question of what works in the particular context. If your system is very, very big, you're going to have a decent amount of requirements because everybody's going to have to be able to work with other people working on different parts of the system. So there's got to be some general understanding of what the system's doing. It's got to be broken up, as we saw, into subsystems. And you've got to have the boundaries between these systems well specified. If it's a small system or a small feature adding on, that's not so much of a problem. The need to interface to other systems, okay? Well, if you need to interface, say client servers need to talk to each other, you're going to have to do specifications of the communication protocol. Okay? Whereas if you were just doing a standalone system, you don't have to talk about that kind of aspect in the requirements. The readership, okay? Is this going to be read by people who are literally end users who know nothing about computers except their own the programs they use on a daily basis? Maybe they know nothing more than how to run a word processor and turn the machine on and off. Okay? Under those circumstances, having extensively detailed requirements that go into a lot of detail will go over their heads and will be pointless. On the other hand, you might have documents that are needed by other engineers. You're creating software for a space shuttle, and all kinds of other engineers are going to be interfacing to aspects of this software. There's going to be extensive detail in the requirements about how all aspects of this work, and all the people working in this system are highly educated people. They're different kinds of engineers, not all software engineers, but they have enough software engineering background but in order to talk to you intelligently and understand your specifications. And by the way, let's just skip down. The cost that would be incurred if the requirements were faulty in a space shuttle is huge. So you have to go into detail to really make sure that you're not going to end up specifying something inappropriately, inaccurately, that's going to result in death or destruction or huge economic cost. Whereas if you're specifying something that, you know, a web-based system for gathering information, as I was last week, from a few users in a form, if it crashes, hey, no problem. They email me and say, I got this thing, I can't type the data in. I say, well, just send me a screen dump of your system, or send me a Word file that has it. It's not a big deal if it goes wrong. Okay? So I didn't put a lot of effort into that because it wasn't worth the effort. Okay? So you have to think, what's the cost that it would be incurred if the requirements were faulty? In a university registration system, the cost could be quite high. It's not a cost in terms of life and death, as in a space shuttle, but if your students can't register, your system goes down for 2 weeks in September, that's pretty hell. It actually happened here. It might not have been requirements, it might have been design. And it wasn't down for 2 weeks, thank heavens, but nevertheless, you know, it caused cost. It caused some students not to get into courses they wanted to, and it caused a lot of headache for professors, you know, dealing with students who came in late, and things like that. Okay? The stage in requirements gathering. As we move down into requirements, our first interviewing and brainstorming sessions will allow us to sketch something out. As we move in more depth, we can add more detail. And level of experience with the domain and the technology. Okay? The concept here is that if I'm developing something which is totally radical and totally new, people haven't developed systems, software systems like this before, we have to explore. We don't know what the requirements really are because nobody's done it yet. Say some physicist comes up with a time machine technology and you have to develop the software to control it, okay? Hey, nobody's done that before. It's really radical, really new, and you're just going to be going along with this physicist developing software as they go, you know, to control the complicated whatever it is that makes it work, okay? If you're developing a payroll system, on the other hand, that's been done lots of times before, so you can go into more detail and specify everything out because it's well understood what the typical requirements for payroll are. Or at least it's well understood if you go and dig up the information with interviews and brainstorming and reading documents and so on. Okay? So the level of detail fundamentally is a cost-benefit decision, and all of these things really bear on cost-benefit. You know, it costs money to develop requirements. It costs money also if the requirements are bad. So we have to get the right level. And it costs money, it wastes money if the requirements aren't used. Balance. A lot of engineering is about balance. Balance between pros and cons. Okay. There's a tendency in the industry for people to say, oh, well, you know, we're just going to go whole hog and develop massive requirements documents. There were some government standards put out in the US years ago that required tremendous detail of specification of how the requirements should be written. These were discredited after a while. People realized that they were wasting vast amounts of money on stuff that nobody ever read, or even if they ever did, it was wasting their time reading it anyway. You've got to right-size them. Reviewing requirements. Later on, we're going to talk about reviewing designs, reviewing code. Reviewing is a fundamental software engineering activity that everybody needs to do sometimes. And organizations probably need to do it more and need to do it in a more disciplined, systematic way than is common. So what you do is you take each individual requirement and you ask yourself, as a reviewer, does it meet each of these criteria on slide 18? First of all, as we just talked about on the last slide, does its benefits outweigh its costs? Think about that. Throw it away if it doesn't. Say, the costs of developing this are going to be too high for the benefits it's going to provide to our end users. It's amazing how many things are developed where the costs are higher than the benefits. It's amazing. Secondly, even if the benefits outweigh the costs, we can't do everything. It might be that we would get a lot of benefit, but we only have a limited amount of time and a limited amount of money to spend initially. We don't want to try and do everything at once, because if we make a mistake, then the whole project could go down the tubes. So we want to start small. So focus on the current problem and do those things that are most important first, and throw away anything that isn't solving the customer's problem. Defer it to another project, even if the benefits outweigh the costs. Put it aside. That can be done by somebody else. Yes, it would be good. Benefits outweigh the costs. But we now want to focus on the current problem. Thirdly, have you written it down in a clear way, in a consistent way, and in an unambiguous way? Okay? We talked about non-functional requirements. Non-ambiguous means you're going to say the response time shall be less than 1 second. Ambiguous might mean, oh, it's going to work fast, you know? Totally ambiguous. Does fast mean response time anyway? Does it mean throughput? What does it mean? Okay? So unambiguous means things are crystal clear. You're not using words that have multiple meanings. Talked about the different meanings of words in classes a while ago, right? Different meanings of bus. Now, that's usually not a confusion when you're writing requirements, but sometimes words can be very confusing. So be careful. Clear and consistent. You know, follow a structure. And logically consistent. Don't contradict yourself. Don't contradict other requirements documents. And when you're reviewing, you want to review to see if there are any inconsistencies and flag them. Are the quality level that we're defining in our non-functional requirements sufficient? We don't want too much quality because that'll cost too much. We don't want too little quality because then we won't get the benefits we want. We want the right level of quality. Is this requirement going to lead to a system of sufficient quality? Is it realistic? Do we have the resources? First of all, do we have the human beings, the software engineers who have the expertise to develop this system? Okay? A couple of years ago, there was a severe shortage of software developers. Even now, there's a shortage of people who have certain kinds of skills. Okay? And so if you can't get people, you can't hire people, there's no point putting requirements down. I mean, maybe you can hire a couple of co-op students, but they don't have the skill to develop certain kinds of sophisticated technology. And if all you can get is co-op students, then you really have to scale back your requirements to something much more minimal. Okay? So do we have those resources? Do we have other kinds of resources? The network bandwidth to support some video application. You know, there's no point proposing to do all kinds of multimedia if we don't have the hardware to support that. Is each requirement verifiable and identifiable? Verifiable refers to numbers on non-functional requirements. Can we test everything? Can we later on say, this has been done, this has not been done? Finally, identifiable. Identifiable is saying, can I point to a requirement by number and sentence number? And you don't have to number each requirement. That becomes excessive. You get nested requirements that look like 1.7.3.2.9. That just clutters the document up. But you can have section 1.3 and third paragraph or third sentence, and each sentence is short, each paragraph is short, or maybe you have bullets. So you say, you know, requirement 9.6, fourth bullet. So you can point to each one. And that's important because you want to be able later on to say in your design which requirements this piece of design implements. Or if there's a bug, which requirements you're referring to. It's like works of Shakespeare. If you read Shakespeare, you'll notice that every single verse is numbered. If you read the Quran or the Bible, you find the same thing. Because these are documents that people are referring to. People are pointing to things in these documents on a regular basis, making quotes out of them. Same thing with requirements. There needs to be a way to make quotes out of things, and therefore they need to be numbered in some systematic way. That's what we mean by identifiable. And finally, each requirement must not over-constrain the design. If the requirement is saying it's going to use this algorithm, that's usually over-constraining design. Okay, we want to leave that to the design stage we'll get to later on. Questions? So we just talked about each individual requirement. The entire document as a collection needs to be complete, sufficiently complete, not excessive, but sufficiently complete, well organized, so you need to figure out a way that groups the requirements together in some logical way. That depends on the system. Clear, people can quickly skim through to find what they want without having to wade through morasses of text that's difficult to figure out. And agreed to. Okay, so all the stakeholders get together and negotiate. Sometimes some stakeholders don't want this, but want something. Some other ones want something else. And eventually, everybody gets together and says, "Okay, well, we're going to do this in the first release, and we'll leave other things to the second release." And another quality is that you want traceability. Traceability is a very important concept in software engineering, and it comes in a number of respects. From the design document we'll talk about later, you want to be able to point to the reasons why you did a certain design decision. The reasons for a piece of design have to do with the requirement. Which requirement does it point to? And also some other rationale, some alternatives that has to do with efficiency or something like that. At the requirements level, we can also have rationale, and we should. In a requirements document, there should be set-aside places where there are paragraphs or introductory material that says, here is some of the thinking that went on when we were developing the requirements. Here's our reasons for choosing these alternatives over these other alternatives. Okay, that's called rationale, and that you can have the rationale in a separate document in some places. In a couple of minutes, we're going to actually look at a real requirements document. The requirements document that I've written for this book have been given headings in the following categories. This is very, very simple. You'll find organizations that have much more sophisticated patterns. Generally speaking, you should follow patterns that your organization uses unless they're excessively detailed, in which case you can argue for simpler approaches. At the very least, there should be some reference to the problem statement. There should be some way that users can go and find the problem. Maybe it's in another document, or maybe it's directly here. There's the background information. There's either links to other background information, pointers to other documents, or, alternatively, you describe here. And this is where a lot of your rationale can go. Here are some thought processes we used. Here are alternatives we considered. Environment and system models is saying, what are the kinds of what exists already that we're going to be putting this system into? What is the existing hardware, the existing network, and so on. For example, if I'm later on talking in my functional requirements about such and such a module going on computer A and such another module going on computer B, well, I've talked about computer A and computer B in my environment and system models. Functional requirements, I talked about those. Input, output, computation, timing, database storage. Non-functional requirements, things like performance, throughput, allowable for future enhancements, etc. Okay, I'm going to now actually just take you directly into the book. Okay, and we're going to take a look at a document that is written in the book that is requirements for a feature of the SimpleChat instant messaging program. This is my manuscript as opposed to the real book. On the video we'll have actual snapshots of the textbook here. Okay, so one of the things that we have in this requirement is a statement of problem. And notice that this problem is focusing on a feature. So it's not the SimpleChat system as a whole, it's a particular feature we're adding to the SimpleChat system. Okay? And it says sometimes the user wants to prevent messages received by a given client from appearing on his or her screen. Okay? So that's that statement of the problem. You know, it's a problem that users have. And then it goes on a little bit more detail, a couple of sentences, but it's a short, succinct problem statement in general. Okay? Then we move on to the background information, and this is where I'm going to be discussing a number of things. First of all, I say, see the requirements for SimpleChat Phase 2. Okay, so that's setting the scene. That's saying, go look at this other document, because that's background information. You've got to read the other document to see the overall requirements for the system. Then I'm saying, here are some issues we considered. Here are some things that we thought about. First of all, can the user block more than one user at a time? It could be yes, could be no. So we thought about that. That was an issue. That was a simple decision. The answer is yes, with a bit more detail. Moving down, we get into some issues like issue 4, where there's several options. Should a server be able to block messages? And option 1 is don't allow, option 2 is do allow, and there are some advantages to each. So we can document our advantages and disadvantages, so that later on, when people are coming to try and understand why we made our decision, they can see why we made our decision. And they won't try and say, oh, that was a wrong decision. If you don't have rationale, people come and say, I don't know why they did that. Looks dumb to me. Let's change it. Right? Whereas if you've actually written down, they can come and say, I don't know why they did that. Looks dumb to me. Let's see why they made the decision. Oh, now I understand. Maybe it's not so dumb. Or, still dumb. But at least I understood what they did. I'm going to add my own rationale that explains why their rationale was wrong. Okay? So that's why we have this rationale in here. And then we move down and we get to the functional requirements. Yeah. Sorry, before that we have system and environment models. That says this feature is to be added to phase 2 of the simple client server system, or SimpleChat. Okay, at the same time as developing some other features. So it says what the context is that we're developing this requirements in. It talks about the functional requirements. And I've organized these in a way that I think is systematic. I've said, first of all, we're going to talk about general ones that apply to both client and server. And within those, we're going to talk about a set of commands. So we have the block command. And it says what basically the block command does, what the output is. Notice I've got input, block user, output, messages from user will be blocked. And there's different kinds of output depending on certain circumstances. Unblock, another command, who I block, who blocks me. Then I have a second section which is operation. This is talking more about the computations that goes on. Under certain circumstances, what will happen? So if I've issued these commands, then from that point on, the system will behave slightly differently, and here's how it behaves. So if X blocks messages from Y, this has the following effects, irrespective of whether X or Y are client or server. I'm being very specific there. I'm saying it works the same way on client and server. So any hash message sent by Y will not reach X, and also any kind of message, by the way, will not reach X, and private messages neither. I'm clarifying. I'm being very specific here, so people don't ask questions. You know, shouldn't be any questions left over at the end, basically. And under certain circumstances, these other messages are displayed, like cannot send message because X is blocking messages from you, and so on. Okay? Non-functional requirements. Oh, wow, this is very short. It says there are none beyond the non-functional requirements that already existed for the top-level requirements document. And that's legitimate. There have to be non-functional requirements, but not necessarily at every level of documentation. Let's go back and look at another document. There's another requirements document in the book. This one is the GANA system, the GPS-assisted navigation assistant for cars. And there's non-functional requirements for that. The first one says the system will be robust in the case of failure of the internet connection or to receive the GPS signal. So it doesn't just sort of say, sorry, can't function, you're lost. Okay? It tries to give you some kind of help. Okay? Now, we could go into more detail. And in fact, it could be argued that this could be turned into a functional requirement that says what actually it does. So sometimes the non-functional requirements are on the boundary. The next one, and a requirements review might detect that. One of the exercises in this book, in fact, exercise 419, is perform a requirements review. We've deliberately seeded this with some issues. Number 2, the system will be designed in a flexible way such that changes in wireless internet or GPS technology can be incorporated. Requirement for future enhancement. One of the key kinds of non-functional requirements, right? So that allows us, the designers, to know that we have to allow for that, and we have to design our system flexibly. The next one is also allowance for future enhancement. It says the system will be designed anticipating incorporation of input from an internal navigation unit, an inertial navigation unit that would take over in cases where GPS signals fail. So that is a strong guidance to our designers. Okay? It's not telling designers what to do, but it's saying, look, we might have an inertial navigation module plugged in later on in a future release. You're going to have to design your core navigation algorithm to take input, either from a GPS or from an inertial navigation system. It might get input from both. All that matters is it's going to get input that says, where are you? Okay, so that there will be some kind of maybe an interface design that is where the system can say, where am I? And it'll either go to a GPS unit or to an inertial navigation unit or both, and you segregated the design up. Okay, so this tells us that as designers we're going to have to worry about that. Any questions? I urge you to read these requirements documents in more detail to learn more about the kind of things you can put there. There's also a microwave oven system described in some detail there as well. Okay, going back to the slide 21. One of the things we have to worry about in requirements is changes. They will change. We want to minimize changes. Part of the work we've done in interviewing, in brainstorming, in prototyping is to get the requirements right so that they don't have to be changed, but they will change. You know, you've done all your work to get perfect requirements, and then the government announces a tax change. That will impact systems that have anything to do with tax, like payroll and so on. Okay, you've got to make a change to your system now. Technology might change. Microsoft might come out with a whole new whiz-bang system that requires you to make some changes to adapt to it. The problem might become better understood. You'd be working away, and after a while the clients come up to you and say, you know, we just discovered some new information, and that causes changes because you want to hopefully take advantage of that information. So requirements analysis should never stop. You should keep communicating with your clients and users as the design goes on. The thing is that you want to minimize the number of changes. You want to get the requirements right as much as possible, but at the same time, as you're doing your design, you want to allow for changes to requirements where possible. If a requirement can be changed relatively easily, and if the cost of making that change is less than the benefit, then you're probably going to make the change. But you're not just going to have the developer say, oh, by the way, thanks, talking to a user, the user wants something, oh, I'll make a change. You're going to go through the process of getting it approved by the stakeholders. It can be a quick process, a quick meeting of requirements, changes that people have asked for in the last week. Can we make them or not? And by the way, as time goes on, each requirement change is going to become more costly. If you specify a requirement at the beginning of the process, it's cheap because you haven't developed the system yet. If you specify a requirement change after you've finished your design and half your implementation, it's much more expensive because then you've got to undo some design, change your implementation plan, and so on. And so what might have been a perfectly viable, cost-effective requirement at the beginning might not be a viable, cost-effective requirement towards the end. In which case you might not approve it. You might say, we're not going to do this. It's going to add extra cost. It's going to slow us down, even if it's relatively small. And sometimes you might say, well, we can do 2 or 3, 4 things that changes, but if we try and do the 25 things they want, that's going to way put us over budget. So we're just not going to do those at this point. And all of these things require intense negotiation and some ability to, get along with people, and perhaps some political posturing, sometimes with different classes of users and customers and managers. That's why a lot of this is human scale kinds of things. The larger the scale changes, the more difficult it should be to get a change request approved. But whatever kind of change request, should be a process for approving it. And that process shouldn't be overly sophisticated. It should be the right level of sophistication. The right level of management should approve the changes. And you want to avoid making the system bigger just for the sake of making it bigger. Defer things to the next release. Keep your system the right size so you get it done on budget. Changes should only make the system better, preferably, not bigger just for bigger's sake. Okay, we'll wrap up by just outlining some of the difficulties and risks that people face when they're doing requirements. First of all, people very often do not have an understanding of the domain, or they do not have an understanding of the real problem. Software engineers often plunge into coding or writing requirements documents without really having a good understanding of what's needed. Okay? So you've got to do those upfront things, interviewing, brainstorming, etc. And prototyping especially. Requirements will change. This is the risk we talked about on the last slide. So make sure that you anticipate that. And the number one thing to tackle potential changes is incremental development. Incremental development says we're going to do a very small system first. This very small system will please most of our users most of the time, but some of the users none of the time, and none of the users all of the time. Okay, you get that? Okay, but the point is it can be done maybe in 2 months with relatively little work. You get it in the hands of the users. And then at least they have something. And if everything else fails from that point on, at least they have something. Whereas if your approach is, we're going to develop everything, a big system with thousands of requirements that will take us 10 months, that's no good. Because then, if you start having problems after 3-4 months, you haven't got them anything. The first approach had something after 2 months. Now you've got problems after 3 or 4 months with the big bang approach. They've got nothing. The system drags on, new requirements get added, and then you decide you're going to have to start all over again because your whole architecture is wrong. They've got nothing. Systems fail. So do things in small increments. Avoid these billion-dollar catastrophes or $1,000 catastrophes of total failures of systems. Also, build flexibility into the design and do reviews. All of these things will help to tackle changes. Don't attempt to do too much. Constrain yourself and stick to those boundaries you set up. Negotiate with people. Go out onto these JAD retreats where everybody can sit and negotiate for a few days away from their regular work. And try and state requirements precisely as you need to, so that there's no ambiguity, and prototyping can often help with that. Okay, so that's it for today, and we'll start chapter 5 first thing on the next lecture.